Quick question. When was the last time every major space agency on Earth simultaneously went silent about the same cosmic event? Take a moment. The answer is never. Not like this. Sure, when Oumuamua passed by in 2017, we saw a flood of data papers and press releases. Same with 2I Boris in 2019, but 3I Atlas, our third confirmed interstellar visitor. We've got fragments, whispers, and a lot of very careful and non-statements. Now, maybe this is just cosmic bad luck timing issues or mundane explanations, or maybe silence is the only logical response when you've seen something you're not quite ready to reveal. Stick around until the end because we're going to calculate how many days of silence it takes before we can't ignore the obvious. If this mystery has got you hooked like it has me, make sure to hit like and subscribe so you don't miss any updates as this unfolds in real time. Drop a comment telling us where you're tuning in, from what time it is, and whether you think we're getting the full truth about 3i Atlas. And if you want to help grow this community, share this video on X, Facebook, Reddit, or even in your group chats. You're the reason we can keep chasing stories like this. Thank you for having our back. Part 1. The Void Speaks Louder. Picture this: a single fuzzy dot on a screen. That's all we have. The European Space Agency captured it during a Mars flyby, a faint smudge against the cosmic backdrop, barely distinguishable from the vast noise of space itself. This is 3I Atlas III, confirmed interstellar visitor to our solar system, photographed from a distance of roughly 29 million kilometers from Mars. It's not much to look at, just a blur, a whisper of light. But here's what makes your skin prickle. That blur is all we've received in the 96 hours, maybe longer, of near total silence from the world's most powerful space agencies. Think about how fast information usually travels in our hyper-connected world. When an asteroid passes by Earth, we get press releases within hours. When a supernova flares in a distant galaxy, astronomers are tweeting about it before the light even reaches us. The machinery of modern space science thrives on immediacy, on sharing, on the rush of discovery broadcast to anyone with an internet connection. So why? When an object from another star system passes through our neighborhood, do we hear nothing? NASA has been eerily quiet beyond their initial announcements. China's space program, silent. The United Arab Emirates, with their Hope orbiter at Mars, hasn't uttered a word about observing it. It's as if someone pressed a cosmic mute button, right, when we should be hearing the most noise. You might think this is just bureaucratic delay. Agencies need time to verify data, run calculations, and ensure they don't embarrass themselves with a false claim. That's reasonable. After all, that's how science works. But here's the thing. We've had interstellar visitors before. When Oumuamua passed by in 2017, the scientific community exploded with activity. Papers were published. Data was shared. Telescopes around the world scrambled for one more glimpse before it vanished into the dark. When 2I Borisov showed up in 2019, we had spectrum analysis, composition estimates, and orbital predictions splashed across the news within days. The system worked like it was supposed to. This time feels different. This time, silence itself has become a character in our story, a presence as palpable as the object we're trying to understand. When absence becomes the loudest signal in the room, you have to ask yourself, what is the absence trying to tell you? Is it caution, confusion, or is it something else entirely? Something so significant that agencies are choosing their words with such care they'd rather say nothing at all. Let me ground you in something crucial. 3. Atlas isn't our first interstellar visitor, but it might be the most significant. The stakes have changed since Oumuamua. Back then, we were like children, encountering something magical for the first time, scrambling to understand what it meant. Now we're older, maybe wearier. We've had time to reflect on what it means when objects from other star systems can reach us, what possibilities that opens up, and what questions it forces us to confront. And maybe that's why the silence feels heavier this time. Perhaps, deep down, we're not sure we want to know the answers. In just a moment, we'll examine that European Space Agency image, pixel by pixel, and uncover why it shouldn't even exist under normal expectations. We'll explore why spacecraft designed to study Mars would bother turning their instruments toward a faint object millions of kilometers away. But before we go there, I want you to sit with this discomfort. If the silence persists, if no new data emerges, and if agencies continue to offer nothing but recycled statements and outdated observations, we edge closer to the worst case hypothesis by default. Not because we want to, not because it's the most likely explanation, but because human minds abhor a vacuum. We will fill silence with speculation, whether we mean to or not. There's a pattern in the history of space science. Sometimes delay breeds rumors. Back in 2011, when Comet Elenin was approaching, there was a gap between observation and official statements. In that gap, the internet spun wild theories. It was going to cause earthquakes. It was being followed by a spacecraft. It was going to pull Earth out of orbit. None of it was true, of course. The comet broke apart before it even reached perihelion. But the silence beforehand, that temporary void of information, allowed speculation to flourish like bacteria in a warm dish. The lesson: when scientists don't speak, someone else will speak for them. So before we assume conspiracy or let our imaginations run wild, let's inspect the evidence we do have. Let's look at that fuzzy dot and understand what it can and cannot tell us. Because if we're going to talk about silence, we first need to understand what was spoken, however faintly, in that single captured image. Part 2, the ESA image that shouldn't exist. Let's talk about the European Space Eyes Mars orbiters. ExoMars, TRACE, Gas Orbiter, and Mars Express are not designed to be cosmic paparazzi. These spacecraft exist for one purpose: studying Mars. The TRACE gas orbiter sniffs the Martian atmosphere, searching for methane and other gases that might hint at geological or biological activity below the surface. Mars Express maps the planet's surface, tracks its weather, probes beneath its soil with ground-penetrating radar. These are specialized instruments, built for a specialized job, like sending a portrait photographer to document geology. They're good at what they do, but what they do is very specific. So when the ESA announced they captured an image of 3I Atlas during its closest approach to Mars on October 3rd, 2025, at a distance of approximately 29 million kilometers, the first question should be how. These spacecraft weren't designed to track extremely faint objects moving through deep space. Their cameras are optimized for planetary observation, for capturing the rusty surface of Mars in crisp detail, not for teasing out the feeble photons bouncing off a distant visitor. It's like using a microscope to look at the moon. Sure, you might see something, but it's not what the tool was built for. What they captured was to be generous, underwhelming, a faint fuzzy blob, no clear coma, the glowing cloud of gas and dust that typically surrounds a comet's nucleus. No resolved tail stretching away from the sun. No distinct nucleus, that solid core of ice and rock we'd expect to see. Just fuzz, just noise made, barely visible. Scientists, even the skeptical ones, describe the observation as challenging, as barely detectable. One researcher called it at the limits of what these instruments can resolve. Another said it was consistent with a very faint coma, but with significant uncertainty. For a comet, which is what 3I Atlas is supposed to be, we expect certain things. Comets are dirty snowballs, frozen remnants from the formation of solar systems. As they approach a star, the ice sublimates, turns from solid to gas without passing through liquid, creating that characteristic coma and tail. We should see jets of dust, asymmetric features, maybe even discrete structures where vents on the nucleus spew material into space. We've seen this countless times with comets in our own solar system. It's predictable. It's understood. So why does 3I Atlas look like someone smudged a charcoal pencil across the sensor? The verified explanations are straightforward. It's extremely dim. It's extremely far away. The exposure time might have been insufficient. Motion blur is a real concern when you're trying to photograph something moving at tens of thousands of kmh. Stacking multiple images to increase signal to noise ratio can introduce artifacts, create false features, or smooth out real ones. All of this is plausible. All of this fits within the boundaries of normal observational astronomy. We're pushing these instruments to their absolute limits. And sometimes at the limits, you don't get clean data, you get ambiguity. But let's walk to the edge of that ambiguity and peer over. What if the fuzz isn't a limitation of our instruments? What if it's a feature, not a bug? Think about signal disguised as noise. If you wanted to hide something in plain sight, making it look unremarkable is pretty effective. A distinct shape, a geometric pattern, obvious structure that would attract attention, but a fuzzy blob that's dismissible. That's exactly what you'd expect from a dim, distant comet that's barely detectable. It blends into our expectations so perfectly that we might not think to question it. I'm not saying 3I Atlas is deliberately hiding. I'm saying the data is ambiguous enough that it could hide something, and we wouldn't know. Maybe there are structural features within that fuzz that we can't resolve with current imaging. Maybe the fuzz itself is engineered a cloud of reflective particles surrounding something we're not meant to see yet. Or maybe it's exactly what it looks like. A comet so far away and so faint that we're lucky to see anything at all. The problem is with this image alone, we can't tell the difference. Scientists hate ambiguity. They want clean data, clear signals, results that point in one direction with confidence. When data sits in that murky middle ground, when it could support multiple interpretations, the instinct is to wait, gather more observations, run more models, check and double etch, check before making claims. And maybe that's part of the silence. Maybe NASA, maybe other agencies, they're sitting on data that's just as ambiguous as this ESA image, and they're trying to figure out what it means before they say anything publicly. Because once you say something, once you put an interpretation out into the world, you can't unsay it. You can't take it back. But here's what bothers me. Even ambiguous data usually generates conversation. Scientists argue about interpretations. They publish competing papers. They debate in conference halls and on Twitter. The process is messy, but it's visible. With 3i Atlas, even that messy process seems muted. It's not that no one's talking, it's that the volume is turned way down, like everyone's speaking in whispers afraid of being overheard. In our next part, we're going to peer into what NASA could have had but hasn't said or might be holding back. We're going to look at the data they've released, the data they've hinted at, and the conspicuous gaps in between. Because if this ISA image is ambiguous, what NASA might have could be far more revealing. The question is whether they're choosing to reveal it. Part 3. NASA's quiet corridors. NASA hasn't been completely silent. Let's be fair about that. They've released materials. There's an animation on their Comet 3i Atlas multimedia page showing the object's trajectory through the solar system. Its hyperbolic orbit clearly indicates it's not gravitationally bound to our sun. There's Hubble imaging from July 21st, 2025, showing what they described as a dust cocoon shape, a roughly spherical cloud of particles surrounding the nucleus. They've issued statements assuring us that there's no threat to Earth, that the orbit has been precisely calculated, and that 3i Atlas will pass through and leave without incident. They've even addressed alien speculation with a spokesperson saying something like, "We follow the evidence, and currently the evidence is consistent with a natural object." All of this is standard procedure. This is what space agencies do. They inform the public, provide reassurance, and present data in digestible formats. But here's where it gets interesting. Look at the timeline. The Hubble observations were made on July 24. They were released when check the dates on the press releases. Calculate how many days passed between the observation and publication. Now compare that to typical Hubble release schedules. Factor in the extraordinary nature of this object. 3i Atlas, the third confirmed interstellar visitor ever detected. Does the timeline make sense, or does it feel stretched? Like someone took the normal process and added a buffer zone, a pause a moment to think before speaking. Then there's the Perseverance incident on October 4th, 2025. Avi Loeb, the Harvard astronomer, who's become something of a celebrity for his willingness to entertain exotic hypotheses, posted an analysis of what he claimed was a Perseverance navcam image showing a stripe, an elongated feature captured by the rover's navigation camera, which Loeb interpreted as possibly being 3i Atlas. The geometry was challenging. The rover is on Mars, and 3i Atlas was tens of millions of kilometers away at that point. Capturing a faint object through Mars's dusty atmosphere with a camera designed for navigation seemed unlikely at best. Skeptics quickly pushed back. Stacking multiple frames to increase signal can produce elongated artifacts, especially if there's any camera motion, or if the object is moving relative to the frame. Exposure time matters too short, and you don't gather enough photons. Too long, and motion blur turns a point source into a streak. The constraints didn't align nicely either. The exposure was too short to detect something that faint, or it was long enough that the object should have appeared as a streak, not a stripe with somewhat defined edges. The debate quickly became technical diving into signal, processing, photon counting, and the specific capabilities of the navcam sensors. NASA never officially confirmed or denied Loeb's interpretation. They didn't release the raw data for independent analysis. They didn't issue a statement saying, "We looked at it. Here's what we think." They simply didn't engage. And that's odd. When a prominent scientist makes a claim about NASA data, even a controversial claim, the agency usually responds. They might say, "We're looking into it," or "Our analysis differs," or even, "We don't have enough information to comment." Silence is not the typical response. So let's reason through what might be happening inside NASA's corridors. Maybe they're verifying the data against multiple sources. Space science is rigorous, and no one wants to announce something significant only to retract it later when better analysis comes through. Maybe there are internal disagreements about how strongly to present any speculative interpretations. Bureaucracies aren't monolithic. Different scientists, departments, and administrators all have their own opinions, and reaching consensus can take time. Maybe data is being intentionally held back until they achieve that consensus, until everyone agrees on what can and cannot be said publicly. Or maybe, and this is where we wade into deeper waters, something was seen that's inconvenient or sensational, and they're waiting for corroboration before speaking. Think about the implications of announcing something truly anomalous. If NASA came out and said, "We've detected features inconsistent with natural cometary behavior," the reaction would be immediate and intense. Media would explode. Social media would catch fire. Every conspiracy theorist would claim vindication. And if it turned out to be wrong, if further analysis showed it was just an artifact or misinterpretation, the damage to NASA's credibility would be significant. The incentive structure pushes toward caution, toward waiting until they're absolutely certain before making bold claims. But caution can look a lot like concealment, especially when the public is hungry for information. The line between responsible science and strategic silence is thin, and from the outside, we can't always tell which side of that line we're on. What we can observe is that NASA's communication pattern feels different this time, more measured, more sparse, more carefully controlled. Whether that's due to scientific uncertainty or something else, we simply don't know. And that uncertainty is only going to deepen as we expand our view, because NASA is not the only player in this cosmic drama. In our next part, we're going to pull back the curtain globally and see how silence is not just NASA's domain. It's a pattern that stretches across national borders, across space agencies, across the entire apparatus of modern astronomy. And when silence becomes a pattern, when it spans continents and institutions, you have to ask whether it's coordinated, whether there's something everyone knows but no one wants to say. Part 4. The Global Curtain. Space is not an American monopoly. Let's establish that up front. The cosmos belongs to everyone, and multiple nations now have the capability to observe, track, and study objects, like 3-Eye Atlas. China's National Space Administration operates a sophisticated array of ground-based telescopes and space assets. The United Arab Emirates has HOPE, their Mars orbiter, which has been sending back stunning data about the Martian atmosphere since its arrival in 2021. The European Space Agency, beyond their Mars orbiters, has access to ground-based facilities across the continent. Russia's Roscosmos, despite being diminished from its Soviet-era prominence, still maintains significant observational capabilities. India's ISRO has made impressive strides in deep space observation. This is a global enterprise, and when something as significant as an interstellar visitor passes through, you'd expect global participation. What we're seeing instead is a chorus of silence. China has not issued any press releases about observations of 3-Eye Atlas. The UAE has not announced any attempts to reorient HOPE's instruments toward the object. ESA released that One fuzzy image we discussed then went quiet. Roscosmos has been focused on its struggling space station ambitions. ISRO has not publicly commented. It's as if everyone simultaneously decided this wasn't worth talking about, which makes no sense given the scientific value of studying an interstellar object. Let's explore possible reasons for this collective quiet. First, technical limitations. Not every spacecraft or telescope is positioned or equipped to observe a faint, fast moving object millions of kilometers away. The UAE's Hope orbiter is optimized for atmospheric studies of Mars, not deep space object tracking. China's space telescopes might not have had a clear line of sight during the critical observation windows. Roscosmos might simply lack the resources or functional assets to contribute meaningfully. These are all legitimate technical constraints. Second, internal policy restrictions or non-disclosure norms. Some nations treat space program activities with significant secrecy. China, for instance, is not known for rapidly releasing scientific data to the global community. Information flows through official channels on official timelines, and those timelines are not dictated by scientific curiosity alone. If China's telescopes observe something interesting, we might not hear about it for months or even years, if at all. This is simply how their system operates. Third, and this is where we enter more speculative territory, coordinated silence. An embargo across agencies, whether formal or informal, where everyone agrees to hold back until certain conditions are met. Maybe until data reaches a threshold of certainty. Maybe until a lead agency like NASA gives the green light. Maybe until diplomatic or security considerations are addressed. Space agencies do coordinate, especially on major projects or discoveries. They share data through agreements that sometimes include provisions about public release timing. The precedent, however, is confusing. When Oumuamua blazed through our solar system in 2017, we saw active international cooperation. Data flowed between agencies. Papers were published rapidly. Different telescopes, different nations, all contributed pieces to the puzzle. When 2I Borisov arrived in 2019, the pattern repeated. Information sharing happened quickly. Press releases coordinated, but did not delay each other. The scientific community operated openly, the way science is supposed to operate. With 3I Atlas, that openness has contracted. There's less coordination visible from the outside, fewer cross announcements, fewer instances of agencies citing each other's observations. It feels more siloed, more insular. Each agency seems to be operating in its own bubble, and those bubbles aren't connecting the way they used to. Whether that's intentional or just an artifact of timing and circumstance, it creates an impression of fragmentation, a system that's not functioning quite the way it used to. Some media outlets have noted these gaps. Articles have appeared asking why China hasn't announced plans to study 3I Atlas with their extensive telescope network. Others have questioned why the UAE, with a perfectly positioned orbiter at Mars, hasn't attempted any observations. The questions are valid, but the answers aren't forthcoming. Official channels remain largely silent on these points. Here's a speculative scenario. Maybe there's an implicit understanding of don't talk until NASA does, a kind of silent running within the international space community. NASA remains the most prominent space agency globally with the largest budget, the most assets, and arguably the most credibility. If NASA is being cautious about how they frame observations of 3I Atlas, other agencies might follow that lead. Not because they're taking orders, but because they're reading the room. They're seeing NASA's measured approach and thinking, maybe we should be careful too. Maybe we should wait and see how this plays out before we stick our necks out. But that creates a feedback loop. If everyone is waiting for someone else to speak first, no one speaks. If everyone is being cautious because everyone else is being cautious, that caution becomes self-reinforcing. The silence perpetuates itself, not because of any conspiracy or coordinated suppression, but because of a collective choice to avoid being the first to make a bold claim. It's like a group of people standing at the edge of a cold pool, each waiting for someone else to jump in first. Is cosmic secrecy becoming a new norm? Are we entering an era where space agencies default to silence rather than transparency, where the impulse to control the narrative outweighs the tradition of open scientific inquiry? Or is this just a temporary aberration, a quirk of this particular observation, and normal patterns will resume once the data is clearer? We don't have answers yet. What we have are questions, and those questions multiply the longer the silence persists. If this silence continues, if no new data emerges from any agency anywhere in the world, the worst case framing begins to loom larger. Not because it's likely, but because human psychology fills voids with fears. In our next part, we're going to confront that worst case scenario head on, not to endorse it, but to understand why it becomes psychologically, if not scientifically, inevitable when information disappears behind institutional walls. Part 5. The worst case scenario frame. Let's say it plainly. If this silence continues, if agencies keep holding back, or saying nothing of substance, the alien hypothesis becomes psychologically inevitable, not scientifically proven, not even scientifically likely, but inevitable in the sense that human minds will drift there. We'll construct that narrative because it's the story that makes the silence make sense. We're storytelling creatures. When we don't have data, we create stories. And the story of extraterrestrial visitation is one of the most powerful stories our species has ever told itself. So let's sketch out what a worst-case scenario might look like, not as a prediction, but as a thought experiment. Imagine 3I Atlas is not a comet. Imagine it's an artifact, something built by intelligence sent into the cosmos, for purposes we don't yet understand. Imagine that agencies detected features, signatures, behaviors that don't align with natural explanations. Maybe there were spectroscopic anomalies, emission lines, that don't match any known comet composition. Maybe there were subtle course corrections, tiny adjustments to trajectory that can't be explained by outgassing or gravitational interactions. Maybe during its passage behind the sun during the period of occultation, when we couldn't observe it directly, something happened that changed its velocity, or heading in ways that violate what comets should do. Now imagine this object is on a trajectory that intersects with the Earth or its orbital path. Not immediately, not in a threatening way, but in a way that suggests intention, targeting, purpose. The worst case scenario is not just that it exists, but that it's coming here, or sending information here, or preparing something here. That would be the kind of discovery that shatters frameworks. Every assumption about our place in the universe would be up for revision. Every question about whether we're alone would have an answer. And that answer would be terrifying, not because aliens are necessarily hostile, but because the uncertainty would be unbearable. Let's place this in historical context. The scientific community has dealt with false alarms before. The wow signal in 1977 A powerful narrowband radio signal detected by the Big Ear telescope looked for a moment like it might be extraterrestrial communication. It was never detected again, never explained satisfactorily. It remains an anomaly, but not proof of anything. Comet Elenin in 2011 became the subject of wild speculation. People claimed it would cause earthquakes, pole shifts, or some other catastrophe. It broke apart before perihelion. It was nothing. Hysteria evaporated. The UFO UAP disclosure process, which has been unfolding in stages over recent years, offers another model. Governments have started releasing previously classified footage of aerial phenomena that can't be easily explained. They're doing it gradually, a controlled drip of information, letting the public acclimate to the idea that there are things in our skies we don't understand before moving to any bigger revelations. It's a careful choreography designed to avoid panic while acknowledging uncomfortable truths. If 3-Eye Atlas is something anomalous, a similar model might be in play. Agencies might be preparing the ground, waiting for the right moment, trying to figure out how to say something without causing mass hysteria or undermining their own credibility. Because here's the thing, if you announce, "We've detected an artificial interstellar object," you can't walk that back. You can't say, "Oops, our mistake," after the entire world has processed that information. The stakes are too high to get it wrong. So the incentive is to be absolutely certain before saying anything. But from the outside, caution and concealment look the same. The public can't tell the difference between "we're being careful" and "we're hiding something." And the longer the silence lasts, the more the second interpretation gains traction. Conspiracy theories don't emerge from nothing. They emerge from the gaps between what people think they should know and what they're being told. When those gaps widen, when the silence stretches, when agencies offer reassurance without offering data, the conspiracy theories write themselves. I want to be clear. This worst case scenario is speculative. It's not the baseline hypothesis. It's not what the data currently supports, but it is a logical endpoint given the current conditions, a place where minds will wander if the silence persists and deepens. An understanding that psychological trajectory is important because it shapes how we interpret everything that comes next. If people are primed to expect the worst, they'll read ambiguity as confirmation. They'll see normal bureaucratic delay as evidence of a cover-up. The perception becomes its own reality. So we acknowledge this possibility as one branch of inquiry. We keep it on the table not as a closed claim, but as an open question, because dismissing it outright, refusing to even consider it, doesn't make it go away. It just pushes it underground, where it ferments into something less rational, less tethered to evidence. Better to bring it into the light, examine it, and understand why it holds psychological power, even if it lacks scientific proof. Now we descend into the details, the data buried in noise, the anomalies that might be signal or might be static. In the next part, we'll look at what amateur astronomers and professional observatories have been quietly reporting, the orbital residuals, the spectroscopic hints, the whispers that circulate beneath the official silence. Because if silence is the public face, noise is the private undercurrent, and in that noise there might be something worth hearing. Part 6, Data Buried in the Noise. Astronomy has always been a conversation between signal and noise. Every photon that reaches our telescopes carries information, but so do the gaps between photons, the moments of darkness, the statistical fluctuations that blur the line between detection and imagination. When we look at 3i Atlas, we're not just looking at an object, we're looking at data streams, orbital fits, spectroscopic signatures, residuals, and tracking calculations. And in those residuals, those tiny deviations from predicted paths, some people are seeing patterns. The Minor Planet Center maintains logs of small body tracking data, and both amateur astronomers and professionals alike contribute observations, feeding into models that calculate orbits with increasing precision. For most objects, the fits are clean observations, match predictions within acceptable error margins. The object moves according to expectations, and astronomers can refine their calculations. But with 3i Atlas, some trackers have noted odd residuals, small non-gravitational accelerations that don't quite fit the standard comet model. These anomalies could be measurement errors. They could be artifacts of combining data from different observers using different equipment. Or they could be real deviations that suggest something about the object's behavior doesn't match our expectations. Non-gravitational forces are common with comets. As ice sublimates on the sunward side, it creates thrust much like a tiny rocket engine. This causes comets to accelerate or decelerate in ways that pure gravitational calculations don't predict. Astronomers have models for this. They account for it when refining orbits. The problem is the magnitude and direction of these forces should correlate with the comet's distance from the sun, its rotation rate, and the distribution of volatile ices on its surface. If those correlations don't hold, if the forces are too strong or too weak, or pointing in unexpected directions, it raises questions. In recent months, some online forums where amateur astronomers gather to share observations and argue about data reduction techniques have been buzzing with claims about 3i Atlas showing unusual accelerations. One user claimed the object exhibited a delta V inconsistent with water ice sublimation alone. Another suggested the trajectory showed periodic corrections as if something were adjusting its course at regular intervals. These claims are at this point unverified. They're based on publicly available tracking data that anyone can download and analyze, but different analysts get different results depending on how they process the numbers. Noise and signal blur together at these precision levels. The question is, are the discrepancies in these residuals telling us something about 3i Atlas, or are they just statistical anomalies that will eventually be explained away? Then, there's the spectroscopy. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its gaze toward 3i Atlas during its approach. The results didn't come directly from NASA, but from secondary sources citing unnamed researchers claiming Webb detected an unusually high carbon dioxide to water ratio, something like 8, one far higher than typical comets. Carbon dioxide isn't uncommon in comets, but ratios that skewed suggest unusual composition, perhaps formation in a different environment, maybe a different kind of ice mixture than what we see in our solar system's comets. Other spectroscopic hints circulated suggesting unexpected emission lines, perhaps from organic compounds that don't match standard comet chemistry. Or maybe those lines are just noise, artifacts of atmospheric correction, quirks of how the telescope's instruments responded to a faint moving target. Some astronomers have made arguments that these signals are meaningful, worth further investigation. Others argue they're just calibration artifacts, the kind of thing that happens when you push instruments to their detection limits. The truth, like most things in science, probably lies somewhere in the middle, But without access to the raw data and the full analysis pipeline, outsiders can't adjudicate these disputes. This lack of access has frustrated many in the scientific community and left the public at large to speculate about the true nature of what Three-Eye Atlas really is. Let's think about what kinds of anomalies would actually point toward an artificial origin. Non-thermal emission would be a major red flag. If Three-Eye Atlas were emitting light or heat in ways that couldn't be explained by reflected sunlight or thermal radiation from a warm surface, that would be deeply strange. A comet's surface might warm under the sun, but it should cool down quickly once it's far enough away. The idea that an object could be emitting energy outside of what's expected without any obvious thermal source would be something truly extraordinary. Doppler shifts in spectral lines could indicate rotation or movement of components, but strange patterns like periodic modulation suggesting structure or machinery would be even more telling. If there were any kind of radio emission, that would be huge. Comets don't broadcast. They don't emit in organized frequencies. If we detected a signal, any signal coming from Three-Eye Atlas, it would shift the conversation from one of scientific curiosity to one of scientific revolution. But we haven't detected anything like that. At least nothing has been publicly announced. The signals we have are ambiguous statistical whispers that might mean something or might mean nothing. And that ambiguity is precisely where controversy lives. Some scientists see evidence worth pursuing, others see noise worth ignoring. The ambiguity fuels debates and drives the narrative, but it also frustrates those looking for a concrete answer. Which observatories or telescopes might hold key data that hasn't been released? Yet JWST is the obvious candidate. It has the sensitivity to detect faint spectroscopic features that other instruments would miss. Ground-based arrays, like the Very Large Telescope in Chile or the Keck Observatory in Hawaii, could potentially contribute optical and infrared observations if they've been pointed in the right direction. The upcoming Vera Rubin Observatory, once fully operational, will have the capability to track thousands of faint objects simultaneously, automatically flagging anything unusual. If Three-Eye Atlas returns, or if similar objects appear, Rubin will catch them early. But for now, we're stuck with fragments, pieces of data that don't assemble into a clear picture. Some pieces suggest a normal comet behaving normally. Other pieces hint at something weirder, something just off enough to make you pause. And without the full data set, without transparency from the agencies that control the best instruments, we can't resolve the contradictions. We're left guessing, filling gaps with speculation, wondering if the anomalies are real or if we're seeing patterns in randomness because we want to see patterns. In the next part, we'll revisit the most provocative voice in this debate, Avi Loeb, the Harvard astronomer who's made a career out of taking anomalies seriously. We'll examine his arguments about Three-Eye Atlas, how his ideas shape the narrative, and why his hypothesis attracts both fierce support and equally fierce skepticism. Because in science, personality matters. The messenger shapes how the message is received, and Loeb is a messenger who divides opinion like few others. Part 7. Revisiting the Loeb hypothesis. Avi Bay is not a fringe figure. Let's make that clear from the start. He is a professor at Harvard University, the former chair of the astronomy department, and the author of hundreds of papers published in peer-reviewed journals. He has received numerous awards and accolades over the years, making him a respected figure in the scientific community. By any conventional measure, he is firmly mainstream. Yet Avibe has become something more than that. He's also become a lightning rod. This is due to his willingness to say things that many of his peers may think but won't voice publicly. He is unafraid to entertain hypotheses that challenge the boundaries of what is considered respectable in scientific discourse. His willingness to consider unorthodox ideas has made him both a celebrated figure and a target. Avibe's rise to fame began with his observations of Oumuamua, an object that passed through our solar system in 2017, marking the first interstellar object ever detected. While most astronomers classified it as an asteroid or a comet and moved on, Avibe noticed something that disturbed him. He observed the trajectory of the object, and it showed slight accelerations that couldn't easily be explained by outgassing, especially because there were no signs of outgassing. The object's brightness fluctuated in a way that suggested it had an elongated shape tumbling end over end. The velocity and trajectory of Oumuamua seemed to fit what one would expect from a deliberate object sent from another star system rather than a random rock ejected from a distant planetary system. In a published paper, Avibe proposed an intriguing hypothesis. Oumuamua could be a light sail, essentially a thin reflective sheet propelled by starlight or laser. Although humans have conceived of light sail technology, it has not yet been built. This hypothesis was scientifically rigorous, mathematically grounded, and testable in principle, but it was also controversial. The reaction from the scientific community was divided. While some praised Avibe for thinking outside the box, others accused him of seeking attention, lowering the standards of scientific discourse and giving credence to pseudoscience by considering exotic explanations when more mundane ones were available. His critics claimed that he was entertaining possibilities that strayed too far from established scientific norms. Now, as we focus on the object known as 3I Atlas, we see a similar pattern unfolding. Avibe has been vocal in his assessment of this object, publishing Q&As and making public statements that urge us to take its anomalies seriously rather than dismissing them out of hand. His core arguments are as follows. The brightness of 3I Atlas suggests it could either be a large object or one with a highly reflective surface. The trajectory of the object is too neat, too precisely aligned with what we would expect from something that might be targeting the inner solar system rather than tumbling chaotically through space. The lack of a coma or tail, or the ambiguity surrounding those features, does not align with typical comet behavior at such a distance from the Sun. Furthermore, Avibe raises the possibility not as certainty, but as a hypothesis that 3I Atlas may have undergone course adjustments during its occultation behind the Sun when we were unable to observe the object directly. These course changes might have occurred undetected, and it's possible we won't be able to detect them after the fact. Additionally, he points out the minimal or absent non-gravitational forces acting on the object. For a comet, the size of 3I Atlas approaching the Sun, we would expect measurable outgassing effects which would influence the object's trajectory. The object should be shedding material creating thrust, and this would show up in the orbital residuals as deviations from the expected purely Keplerian motion. If these forces are smaller than expected, or if no evidence of them can be detected at all, it's worth investigating further. Either the object is composed of something unusually refractory, such as ices that don't sublimate easily, or it is not composed of ice at all. As expected, the scientific community's response to Avibe's arguments regarding 3 Atlas has been mixed, and many astronomers maintain that the observations still align with the comet and that the anomalies Avibe highlights can be explained by dust behavior, calibration, uncertainties, or simply the limitations of the data available. One researcher was quoted saying something like, "Extraordinary claims require extraordinary evidence, and what we have is ordinary evidence of an ordinary object observed under difficult conditions." Another pointed out that interstellar space, where 3I Atlas comes from, is fundamentally different from the environment in which comets in our own solar system formed. Therefore, we should expect to see compositional differences, unusual ice mixtures, and behaviors that don't fit the templates we use for objects from our local solar system. The debate about 3I Atlas is not just scientific, it has a political and professional dimension that's impossible to ignore. Exotic hypotheses attract attention, media, coverage, book deals, speaking invitations, but they also attract skepticism and professional risk. If you're wrong about something exotic, you risk tarnishing your reputation far more than if you're wrong about something mundane. Peer review becomes harder when your hypothesis is controversial, and funding agencies are less likely to support research they perceive as speculative or unserious. In many ways, modern science has become incentivized to favor conservatism, to stick with explanations that fit within established frameworks and avoid straying too far from the norm. Avibi is aware of these dynamics and has written extensively about them. He argues that science has become too conservative, too quick to dismiss anomalies, and too attached to consensus thinking. He frames his approach as being similar to that of Galileo, a return to a time when scientists were willing to challenge established beliefs based on observational evidence. Critics, however, see his approach differently. They accuse him of attention seeking, of lowering the standards of scientific discourse, and of conflating possibility with plausibility in ways that mislead the public. But here's the key point. Regardless of whether Avibe's specific hypotheses prove correct, the anomalies surrounding 3I Atlas force us to refine our methods. Even if 3I Atlas turns out to be a perfectly normal comet with slightly unusual composition, the process of investigating it, ruling out exotic explanations, and pushing our instruments and models to their limits makes us better scientists. We learn more about what comets can be, how interstellar environments differ from our own, and what signatures we should expect from truly anomalous objects if they ever appear. Avibi often frames his work as a lesson. He argues that we should use objects like 3I Atlas as opportunities to think critically about what we'd look for if we were searching for extraterrestrial technology. What would the signatures be? How would we distinguish artificial from natural objects? What observations would conclusively confirm or rule out intelligence? These are valid scientific questions worth pursuing, even if in this case the answer turns out to be just a comet, because the next object might not be. If we haven't thought through the methodology, if we haven't prepared ourselves mentally and technically, we'll miss it or dismiss it too quickly. The tension between Avibe and the broader scientific community highlights a deeper debate about how science should operate. Should we be conservative, demanding overwhelming evidence before considering exotic explanations? Or should we be more exploratory, willing to entertain unusual hypotheses, as long as they're testable, using them to drive further observation and analysis, even if they're unlikely? Both approaches have merit, and both have risks. Too much conservatism means we might miss genuine discoveries because they don't fit within our expectations. Too much openness means we risk wasting time and resources on chasing phantoms, diluting the credibility of science with speculation. Three-eyed Atlas sits right at the heart of this tension. It's strange enough to warrant attention, but also normal enough to be dismissed. Abibe and others like him push for greater attention, while critics urge caution. The truth is likely somewhere in the middle, waiting for better data to reveal itself. But that data needs to be collected, and those observations need to be made. And someone has to be willing to look, even if looking means being wrong. In the next part, we'll shift our perspective and consider who else might be watching Three-Eye Atlas players beyond government space agencies, private observatories, and commercial networks. There are entities that may have seen something but chosen to stay quiet for their own reasons. Because in the modern world, space observation is no longer a monopoly. The tools are distributed, the observers are many, and information doesn't always flow through official channels. Part 8. Hidden Players. The romantic image of astronomy as the work of a lone scientist peering into the night sky, notebook in hand, is outdated. Modern astronomy is far more industrial and automated. Telescopes now scan the sky, continuously feeding massive amounts of data into processing pipelines that handle millions of observations per night. But not all of these telescopes are government-owned. Not all of the data flows through official channels. The democratization of space observation has created a parallel universe of independent observers, and some of these watchers might know things that haven't made it into press releases. In recent decades, private observatories have proliferated, operated by wealthy individuals, universities, and research consortiums. These entities have built facilities with capabilities that rival those of government-run installations. The La Sombra Observatory, for example, operates a global network of robotic telescopes that can be tasked with custom observations. Planetary resources before it pivoted away from asteroid mining developed techniques for tracking small bodies with commercial imaging systems. And then there are amateur astronomers equipped with CCD cameras and sophisticated software who regularly discover supernovae, asteroids, and comets. The line between professional and amateur astronomers has become increasingly blurred. The distinction now hinges more on funding than capability. Could any of these private entities have observed Three-Eye Atlas in ways that revealed something unusual? It's plausible. A well-equipped amateur with a 16-inch telescope and a cooled CCD camera can detect objects fainter than what was visible to professionals just 50 years ago. Networks like the International Astronomical Union's Minor Planet Center rely heavily on amateur contributions for tracking data. If an amateur astronomer captured something anomalous, a structural feature, an unexpected emission, or a deviation from the predicted position, they might have reported it through official channels. Or they might have kept it to themselves, unsure of what they were seeing, unwilling to make claims without confirmation. There are rumors circulating in online forums, whispers that get scrubbed or deleted. One person claimed they captured an image of Three-Eye Atlas showing bifurcation, as though the object had split or had multiple components. The post was immediately challenged with arguments erupting about whether the observed features were artifacts or genuine. Then the original post was deleted. Another user claimed their automated all-sky camera caught an anomalous brightening event, a sudden spike in luminosity that didn't match impact. or outgassing models. That post also disappeared. Are these real observations that were suppressed, either self censored by nervous observers or removed by moderators trying to keep speculation under control? Or were they hoaxes, attention seeking fabrications that got called out and deleted in shame? We can't know without access to the original data. And that's the problem. In the age of information, data can vanish just as easily as it appears. Screenshots prove nothing. Eyewitness accounts hold no weight without corroboration. The signal to noise ratio in online astronomy communities is so high that it's often difficult to separate genuine anomaly reports from noise. Let's widen the scope. Spacefaring corporations now have assets in orbit that are not primarily scientific instruments, but which could potentially observe deep space objects opportunistically. SpaceX operates thousands of Starlink satellites. Blue Origin is developing orbital infrastructure. Chinese private space firms are launching commercial payloads. These satellites are equipped with cameras, sensors, and communication arrays. Most are pointed at Earth or at each other, but some do have wide-field cameras for navigation, orbital debris, monitoring, and situational awareness. Could any of these systems have captured 3-eye atlas? The geometry would have to align perfectly. The object would need to pass through a satellite's field of view at a time when the camera was active, and the exposure settings were suitable for detecting faint objects. It's a long shot, but not impossible. And if it happened, if a commercial satellite captured imagery of an interstellar object showing something unexpected, what would the company do with that information? Would they release it, publicly sell it, keep it proprietary, or use it for internal research? There's no legal obligation for commercial entities to share astronomical data. They are free to do whatever they want with their observations. Then there's the possibility of secret radar or LiDAR experiments. Deep space radar systems are theoretically capable of detecting and profiling objects at vast distances much farther than optical telescopes can resolve. The Arecibo Observatory, before its collapse, was able to bounce radar signals off near-Earth asteroids and create detailed surface maps. Smaller radar systems exist, some operated by defense departments, some by research institutions, and others by entities that do not advertise their capabilities. If 3-eye atlas passed close enough to Earth and someone pointed a powerful radar system at it, they might have obtained range Doppler imagery showing its shape rotation and surface features. Would such data be made public? Probably not. Radar systems used for space surveillance are often dual use, meaning they track satellites, debris, and potentially adversarial spacecraft as well. These systems are classified, and the data they collect is often classified too. Not because the object itself is a secret, but because revealing the data would also reveal the capabilities of the radar systems, something that is closely guarded for national security reasons. This is standard operational security, not a conspiracy. But from the outside, it creates another black box, a place where information might exist but remains hidden. Communication satellites could also play a role here. These satellites monitor vast swathes of the radio spectrum, looking for signals interference, or anything that might affect their operations. If 3-eye atlas were emitting radio waves faintly or intermittently, a communication satellite might detect it as anomalous background noise. But would that data be made? Public communication companies aren't in the business of astronomy. They would have no reason to analyze or share such data unless it directly impacted their services. The data might sit in logs somewhere unexamined and unreported. Historical analogies help put this in perspective. During the Cold War, early satellite imagery was classified for decades. The technology to photograph Earth from space was revolutionary, and governments didn't want adversaries to know the resolution, coverage, or capabilities of these new tools. Dual use information data with both scientific and military applications is handled cautiously. 3i Atlas is not a military target, but the systems used to observe it might be sensitive, and that sensitivity creates barriers to transparency. So we're left with a landscape where information might exist in corporate servers, classified databases, amateur hard drives, and logs that no one has bothered to examine or share. The official narrative, the one told through press releases and scientific papers, is always incomplete. It's the tip of the iceberg. Below the surface, there is an entire ecosystem of observation and data that never makes it into the public discourse. Could some players already know more than the public knows? Could they be waiting to reveal it or even monetize it? The incentives are different for everyone involved. A corporation might wait for the right moment to announce a discovery, using it for marketing or investment opportunities. A defense agency might never reveal anything, keeping the data locked away indefinitely. An amateur astronomer might have captured something significant, but lacks the credibility or platform to get anyone to take it seriously. The ecosystem is fragmented, and fragmentation creates gaps where information hides. In our next section, we'll explore why global powers might choose strategic silence over open disclosure. We'll move from technical possibilities into the realm of strategy politics and the complex calculations governments make when faced with information that could disrupt societies or reveal capabilities they'd rather keep hidden. Because silence is not always about uncertainty, sometimes it's about control. Part 9: Cosmic Conspiracies. Let's ask the uncomfortable question directly. Why would governments or space agencies stay silent about 3i Atlas if they knew something significant? We've danced around this question in previous parts, but it's time to confront it head on. Not because conspiracy is the most likely explanation, but because understanding the incentives for secrecy helps us interpret the patterns we're seeing. Governments don't operate solely on scientific principles. They base decisions on strategic calculations, risk assessments, and political considerations, things that have nothing to do with the truth and everything to do with control. Let's break down some possible motives for why governments might choose to remain silent. First motive: controlling the narrative and public reaction. Governments are obsessed with managing how information flows to the public. This isn't inherently sinister. It stems from the belief that people may panic or react irrationally if given certain information without proper framing. If 3i Atlas displayed features suggesting an artificial origin, imagine the reaction. Stock markets would likely fluctuate, uncertain about what this means for humanity's future. Religious institutions would scramble to integrate this information into their worldviews, and political movements might form around competing interpretations, some demanding immediate disclosure, others urging preparedness for potential threats. Managing this chaos becomes a powerful incentive to say nothing until the narrative is clear and controlled. Second motive: avoiding mass speculation. Even without concrete evidence of anything anomalous, the mere suggestion that an interstellar object might be artificial would trigger speculation far beyond what evidence supports. We've seen this with the UAP disclosures. The Pentagon released videos of aerial phenomena they couldn't explain, and immediately the public conversation leapt to aliens, even though officials carefully refrained from making that claim. With Three Eye Atlas, if agencies suggested anything unusual, speculation would explode and walking it back later would be nearly impossible. It's far easier to stay silent until the evidence is strong enough to replace speculation with fact. Third motive: protecting sensitive defense or communication interests. Space-based observation systems are often dual use. They monitor asteroids, but also track satellites, debris, and potentially adversarial spacecraft. If Three Eye Atlas were observed by classified systems, revealing what those systems saw could expose their capabilities, things like resolution, sensitivity, and technical features that adversaries could exploit. If the object is scientifically interesting, but not strategically relevant, the data might eventually be declassified. However, if it has national security implications or reveals sensitive collection methods, it could remain classified indefinitely. The systems used to observe the object might have national security dimensions, and this creates barriers to transparency. Fourth motive: buying time to confirm or debunk evidence. Science takes time, and verification takes even longer. If initial observations suggested something anomalous, responsible agencies would want to check, double check, and triple check before making public statements. They'd seek multiple independent confirmations and rule out possibilities like artifacts, instrumental errors, or misinterpretations. This verification process could take weeks or even months. During that time, staying silent is the conservative choice. It's the safe option, even if it frustrates the public and fuels more speculation. Fifth motive: diplomatic and strategic positioning. If Three Eye Atlas represents something genuinely anomalous, different nations might want to position themselves advantageously before any information becomes public. Perhaps China wants to complete its own analysis before NASA announces its findings, so they're not seen as reacting to American claims. Or the United States might want to coordinate with its allies before going public, ensuring a unified message. These strategic calculations can delay disclosure, not because of a conspiracy, but because of the complex dance of international relations. Now let's introduce the black budget possibility. Defense departments around the world operate programs that don't appear in public budgets and have minimal oversight. These programs exist in legal gray zones away from the public eye. The United States Department of Defense has historically run programs tracking objects in space, both terrestrial and otherwise. The Advanced Aerospace Threat Identification Program, AATEP, revealed in 2017, was one such initiative focused on aerial phenomena. But are there equivalent programs focused on deep space objects? Almost certainly. They might not be labeled as such, but the capability exists. If such a program detected something significant about Three Eye Atlas, would we ever hear about it? That depends entirely on what they detected and the strategic value of the information. If it's scientifically interesting, but not strategically relevant, the information could eventually be declassified and made public. If it has strategic implications or national security ramifications, however, it could remain classified indefinitely. The absence of information is not evidence of absence when classified programs are involved. Historical parallels show us this dynamic clearly. During the Cold War, reconnaissance satellites were so secret that their very existence was classified for years. Data they collected, though scientifically valuable, stayed locked away because it could expose military capabilities. UFO and UAP programs in the 20th century operated with minimal oversight, releasing information only sporadically and often under pressure from leaks or Freedom of Information Act requests. When national security is involved, transparency suffers even if the object itself is scientifically significant. 3I Atlas. Despite being a natural or potentially natural object, intersects with space surveillance systems that have significant national security dimensions, which makes full openness difficult. Let me walk through a hypothetical scenario. Imagine a classified detection occurred in observation by a system that officially doesn't exist or whose capabilities aren't publicly known. This observation might show something unexpected. Maybe surface features inconsistent with a comet, maybe a faint emission in an unexpected wavelength, or maybe trajectory adjustments that need explanation. What happens next? First, the data is flagged and escalated. Someone decides it's significant enough to brief higher ups. Then, verification begins. Other systems are tasked with corroborating the findings, checking for artifacts, and ensuring the data is valid. If verification holds, the next step is a discussion about what to do with the information. Legal experts weigh in on classification requirements, while scientific advisors assess whether civilian astronomers might independently discover the same anomaly. Strategic planners then consider the geopolitical implications and public affairs. Officers begin drafting statements, preparing to manage the disclosure process. This process takes time, weeks, or even months. During this period, agencies like NASA may be informed, but they'd be constrained by what they can publicly say. They can't reference classified information or hint at sources they're not authorized to acknowledge. As a result, they either say nothing or issue bland reassurances based only on unclassified data. To the outside world, this might look like concealment or incompetence, but from the inside, it's simply standard procedure. Eventually, one of two things happens. Either the anomaly is explained away, labeled as instrumental error or a natural phenomenon, and the data stays classified, or the anomaly persists, gains weight, and a decision is made about managed disclosure. In that case, information would be released gradually and carefully, with statements carefully coordinated across agencies and possibly across nations. The public would be told a story that is true but incomplete, designed to inform without revealing sensitive capabilities. Is this happening with 3I Atlas? We don't have definitive evidence that it is, but we don't have evidence that it isn't either. The infrastructure for exactly this kind of scenario exists. The precedents exist. The incentives exist. Whether or not these elements have combined in this case remains speculation, but it's informed speculation based on how governments and agencies actually operate, not unfounded conspiracy. Counter arguments are important here. Transparency pressure is real. In democracies, governments face oversight leaks, whistleblowers, and journalists who dig for buried stories. Scientific peer review creates its own transparency imperatives. If NASA scientists know something significant, many of them would want to publish their findings regardless of what officials might prefer. Leaks happen. The Pentagon papers were leaked. Edward Snowden leaked documents. Even classified space programs have been revealed through leaks and investigative reporting. Perfect secrecy is nearly impossible to maintain over the long term. So if there's something significant about 3I Atlas, if agencies are sitting on anomalous data, the silence likely won't last indefinitely. Eventually, someone will talk, someone will leak, someone will publish. The question isn't if the silence will break, but when and what happens to the information in the meantime. In our next part, we're going to shift gears entirely. Moving away from intrigue and government secrecy, we'll explore the theory of Three-Eye Atlas as an alien artifact. What does silence itself reveal about its design purpose and the constraints placed on its makers? We'll delve into speculative physics, asking how a probe's quietness might reveal the intentions and capabilities of its creators. Because sometimes the absence of a signal is the signal. Part 10, the speculative physics of silence. Let's engage in a thought experiment. For the next few minutes, let's assume Three-Eye Atlas is not a comet. Let's assume it's an artifact, a probe sent by an intelligence from another star system. Now ask yourself, what does its silence tell us? Not the silence of governments, but the silence of the object itself. Why would an interstellar probe designed to explore or observe remain completely quiet, emitting no signals, making no attempts to contact us, and appearing merely as a faint fuzzy blob in our telescopes? The first answer is stealth. If you wanted to observe without being noticed, you'd minimize every detectable signature. No radio transmissions, because those would announce your presence across vast distances. No unnecessary thermal emissions, because heat is detectable in infrared. No bright surfaces or reflective panels, because they would catch sunlight and draw attention. You design the probe for minimal visibility, making it appear as much like a natural object as possible. A stealth probe would likely have a dark, non-reflective hull. It might be covered in materials that absorb light rather than reflect it. Instead of active cooling, it might use passive methods, radiating heat slowly and in directions away from potential observers. This design makes sense if the probe's purpose is to observe without interference. Perhaps its creators want to study civilizations without contaminating the study by introducing the variable of contact. We do something similar with wildlife observation. We use camera traps, remote sensors, and other techniques that let us watch animals without them knowing we're watching. A probe operating on the same principle would stay hidden, gathering data silently and reporting back through channels we can't detect. The second answer is energy conservation. Interstellar travel is immensely expensive in energy terms. Accelerating even a small mass to a significant fraction of light speed requires enormous amounts of energy. A probe might not carry enough fuel or power generation capacity to actively signal, especially if it's meant to operate for centuries or even millennia. Instead, it might rely on passive data collection, storing information, waiting for a rendezvous with another probe or a mothership, or simply recording for its own purposes without needing to transmit immediately. Passive power scavenging fits this model. The probe might harvest energy from starlight through ultra-efficient solar panels or collect particles from the interstellar medium. Alternatively, it could use radioactive decay of on-board materials, generating a slow and steady trickle of power. All of these methods provide limited energy, enough for basic functions, but not enough for high-power transmissions. The probe remains quiet because it has no choice. It operates on an energy budget where every watt counts and every function is optimized for efficiency over communication. The third answer is AI-driven autonomy with specific mission parameters. Imagine the probe is intelligent, equipped with artificial intelligence capable of making decisions but constrained by programming that dictates its behavior. Its instructions might be simple: observe but don't contact. Collect data on planetary systems, on technological civilizations if encountered, but maintain a safe distance. Report findings only under specific conditions, or never report at all if the mission is purely archival. An AI probe doesn't have curiosity or desire, it simply follows its programming. If that programming says, stay quiet, it stays quiet. This idea ties into concepts from the CTI and the Fermi paradox. The zoo hypothesis suggests that extraterrestrial civilizations might be deliberately avoiding contact with us, treating Earth like a nature preserve, observing us without interfering. A probe operating under the zoo hypothesis would be designed for observation without direct interaction, explaining both its presence and its silence. Another related idea is the lurker hypothesis. Perhaps probes are scattered throughout the galaxy, dormant, waiting for specific triggers before activating. Maybe the trigger is a technological maturity, the moment a civilization develops certain capabilities. Maybe the trigger is a signal we're supposed to send. Until the trigger condition is met, the probe remains silent. Cryptographic or quantum communication offers another explanation. If the probe is transmitting, it might be using methods we don't yet have the technology to detect. For example, quantum entanglement could allow instantaneous communication without classical signals traveling through space. Highly directional low-power laser links could send information in narrow beams, which we'd never intercept unless we're directly in line with the target. Spread spectrum techniques could distribute a signal across a wide frequency range, making it look like noise, unless you know the decoding key. Human radio and television broadcasts leak into space, creating a detectable signature for any civilization with sensitive receivers. But this is inefficient, the equivalent of shouting when you could whisper. An advanced civilization would likely use communication methods that minimize leakage and direct information precisely where it needs to go without wasting energy broadcasting to the void. From our perspective, such communications would be indistinguishable from silence. The probe might be chatty, just not in a way we can hear. Energy constraints highlight why silence might be the optimal strategy. Interstellar space is cold close to absolute zero. Any active system generates waste heat, and disposing of that heat without radiating detectable signals is challenging. A probe might use radiators pointed away from likely observers, shedding heat into the cosmic microwave background. It might operate at very low power, processing data slowly and waiting long periods between active phases. All of this minimizes heat emissions and any detectable signature. Could this explain why we only see a faint blob? Perhaps the blob is deliberate, a minimal surface, reflecting just enough light to look comet-like, while hiding the probe's actual structure beneath layers of dust or ice. This natural camouflage could have accumulated over the probe's journey through interstellar space. Alternatively, the fuzziness could be a cloud of particles the probe generates to obscure itself, a dust screen making detailed imaging impossible. We're not seeing the probe itself, we're looking at the camouflage. These ideas are speculative, but they are grounded in known physics, not fantasy. We know how to build probes that minimize emissions. We understand stealth technology, passive observation, and energy constraints. Extrapolating these principles to an interstellar context is reasonable and helps us think through what artificial objects might look like so we know what to search for. This speculation serves a purpose. It sharpens our observational strategies. If we think a probe might use quantum communication, we develop quantum detectors. If we think it might radiate waste heat in specific directions, we position observers to catch those emissions. If we think it might be hiding under dust, we develop techniques to penetrate that dust with radar or other wavelengths. Even if 3i Atlas is just a comet thinking through these scenarios, prepares us for the real thing, if it ever arrives. Now we're going to shift away from 3i Atlas for a while. We'll scan the wider frontier of 2025 science, looking at other anomalies, other silences, and other places where the cosmos whispers and we struggle to interpret its messages. Because 3i Atlas is not happening in isolation. It's part of a larger pattern of mysteries, discoveries, and questions that define our current moment in scientific history. Understanding that context will help us see 3i Atlas more clearly and see how it fits into the bigger picture of our cosmic awakening. Part 11: Solar Superstorms and Hidden Risks. The sun tried to remind us who's in charge during May and June of 2025. Coronal mass ejections, CMEs, massive eruptions of plasma, and magnetic fields from the sun's surface slammed into Earth's magnetosphere with such force that global geomagnetic alerts were triggered. The skies erupted in colorful auroras dancing at latitudes far south of their usual range. Satellite operators scrambled to protect their assets. Power grid managers nervously watched, ready to implement emergency protocols if things worsened. For a few days, the threat was real. Not existential, but significant. The kind of event that could knock out communication satellites, disrupt GPS damage, transformers and power grids, and potentially plunge entire regions into darkness for weeks or even months. A coronal mass ejection is a powerful phenomenon. The sun ejects billions of tons of charged particles into space at speeds approaching 1,000,000 miles per hour, sending them hurtling towards Earth. The Carrington event in 1859, the most powerful geomagnetic storm in recorded history, induced currents so strong that telegraph systems sparked and even caught fire. The potential consequences of a similar event today, with our vastly more complex and vulnerable infrastructure, could be catastrophic, reaching trillions of dollars in damage and affecting billions of people across the globe. Here's why this matters to our larger story. Space threats like CMEs exist on a spectrum, and space agencies treat them conservatively. The sun, while predictable in some ways, is wildly unpredictable in others. We can track CMEs as they leave the sun and predict when they'll hit Earth, but we can't always predict their intensity or their exact magnetic orientation, which determines how much damage they'll cause. Despite this uncertainty, space weather agencies issue alerts, warnings, and forecasts. They communicate because the threat is understood, the physics behind it is known, and the response protocols are already well established. Now contrast that with 3i Atlas, an object we don't fully understand, exhibiting behaviors that may or may not be anomalous, approaching the inner solar system with no clear threat, but plenty of ambiguity. How do space agencies handle that? They treat it conservatively, meaning they say very little until they know more. They don't want to alarm the public over something that might turn out to be nothing. They don't want to incite panic or speculation without concrete evidence of danger or significance. So they default to silence, or they issue bland reassurances that communicate nothing of substance. This is a pattern that we can observe. Known threats generate communication, while unknown or ambiguous threats generate silence. It's a risk management strategy. Talking about a coronal mass ejection is safe because everyone understands the threat is natural, temporary, and manageable. Talking about an interstellar object that might be anomalous opens doors to questions that agencies aren't prepared to answer. What if it's artificial? What if it changes course? What if there are more like it? It's better to say nothing than to trigger those questions prematurely. In 2025, new solar weather forecasting research has made predictions about solar activity more accurate. Machine learning models trained on decades of solar observation data can now forecast CME intensity with greater confidence. Satellite constellations monitor the sun continuously from multiple angles, providing stereoscopic views that help predict how ejected material will evolve as it travels toward Earth. These advances give us more warning time, more accurate predictions, and better abilities to protect our infrastructure. And this information is shared openly, published in journals, discussed at conferences, and integrated into public forecasting systems. Why the difference? Because solar weather is a known quantity, a threat we've domesticated through understanding. We've learned to predict it with reasonable accuracy, and we've developed protocols to manage it. 3I Atlas, on the other hand, represents the unknown, the undomesticated. It belongs to the category of things we haven't learned to manage yet. Humans, scientists, and bureaucrats alike handle the unknown differently than the known. The unknown gets quarantined, kept at arm's length, and studied cautiously before being integrated into public discourse. The cosmos is noisy. Signals bombard us constantly. Radio waves from distant galaxies, neutrinos from supernova, gravitational waves from colliding black holes, and the hiss of the cosmic microwave background radiation. Most of this noise we ignore because it fits our models because it's expected. But when something doesn't fit, when a signal arrives that challenges our frameworks, the noise becomes deafening in a different way. It's the noise of speculation, of competing interpretations of uncertainty that resists resolution. And sometimes the response to that noise is to mute the conversation until clarity emerges. 3I Atlas is one note in that cosmic symphony. Solar storms are another. We are at a crossroads. The world of science and discovery is brimming with anomalies and possibilities, some that might change our understanding of the universe. Yet the institutions that are supposed to uncover these truths are faced with an intricate web of risk, responsibility, and control. The way we handle 3I Atlas could ultimately set the stage for how we handle future cosmic events. What happens when we truly confront the unknown? In the coming section, we'll shift our focus to dark matter, another cosmic anomaly that exists in the zone between detection and confirmation, where physics pushes against the boundaries of what we can observe and understand. Dark matter, the biggest invisible presence in the universe, presents a similar challenge to our scientific models and perceptions. We can't see it directly, but we know it's there because of the effects it has on other objects. This is the realm where our understanding of physics is stretched to its limits, and where mysteries like 3I Atlas might just lead us to new discoveries. Understanding dark matter and the ways in which we struggle to confirm its existence might help us see 3I Atlas more clearly. It might even offer insights into how to approach cosmic anomalies, how to adjust our approach to observing, studying, and interpreting the vast, mysterious universe that surrounds us. Because as we continue to explore, it's not just about answering questions, it's about how we learn to ask the right ones. Part 12, Dark Matter. Signal Tease. Deep underground, shielded from cosmic rays by miles of rock, sensitive detectors wait in the dark. These instruments cool to temperatures near absolute zero, sight in quiet anticipation, watching for somethings that may never come. They're hunting dark matter, the invisible substance that makes up 85% of the matter in the universe, yet has never been directly detected. We know dark matter exists because we can see its gravitational effects. Galaxies rotate too fast for the visible matter they contain. Galaxy clusters hold together despite not having enough mass in stars and gas. Gravitational lensing bends light in ways that require more mass than we can see. Something is out there, something with mass, something that doesn't emit or absorb light. We call it dark matter, but that's merely a placeholder for our ignorance. In 2025, whispers have emerged from these underground facilities. Not confirmed detections, not publishable results, but anomalies, clusters of events that don't quite fit expectations. One detector in Italy, the Eiston collaboration, or one of its successor experiments, reported an excess of events within a specific energy range. The excess was small, barely statistically significant, the kind of thing that could be explained by contamination, calibration drift, or random fluctuation. But it was there, persistent, across multiple data runs, enough to make physicists pay attention without getting overly excited. Dark matter particles, if they exist, would pass through ordinary matter almost without interaction. Only occasionally, maybe once every few months, in a ton of detector material, would a dark matter particle collide with an atomic nucleus, producing a tiny flash of light or a minute energy deposit. That's what these underground detectors are designed to catch, those incredibly rare collisions. Signals so faint they barely rise above the noise. Distinguishing a real dark matter signal from background noise requires years of data, exquisite calibration, and multiple independent confirmations. The whispers from 2025 don't constitute confirmation. They're tantalizing hints, possibilities that need more time, more data, and more scrutiny before anyone will call them a discovery. But they're not nothing. They're the kind of anomaly that drives physicists to check their instruments, reanalyze their data, and consider whether they've just captured the first faint signature of something real. To explain this to a general audience, imagine trying to hear a whisper in a crowded stadium. That whisper is dark matter. The crowd noise is everything else. The background radiation, cosmic rays, radioactive decay from the detector materials, and every other source of energy that creates signals. To hear the whisper, you need to eliminate as much of the crowd noise as possible. You go deep underground to block out cosmic rays. You use ultra-pure materials to minimize radioactive contamination. You cool everything to reduce thermal noise. You run the detector for years, accumulating data, waiting for the statistics to improve, enough that a real signal, if it exists, will emerge from the noise. Now let's connect this to 3i Atlas. Both are stories about signals hiding in noise, about anomalies that might be something or might be nothing, about the difficulty of distinguishing the real from the artifact when you're operating at the limits of detection. Dark matter experiments are designed with this very challenge in mind. They build in redundancy multiple confirmation methods and strict statistical thresholds before claiming a discovery. The process is slow, deliberate, and conservative. Astronomy doesn't always have that luxury. 3i Atlas passed through the inner solar system on a schedule we didn't control. We got one chance, maybe a few weeks of optimal observation, and then it was gone. The data we've collected is all we'll have unless 3I Atlas comes back, which seems unlikely given its hyperbolic trajectory. So the evidentiary standard is different. We can't wait years for confirmation, like dark matter experiments can. We have to work with what we've got, interpret it as best as we can, acknowledge the uncertainty, but still draw conclusions. This creates a symmetry in how discoveries are announced. Dark matter experiments can afford to wait and say, we saw something interesting, but we're not calling it a detection yet. Astronomers observing a transient object don't have that luxury. They also face intense pressure not to overclaim, not to announce something dramatic that later falls apart. The result is a middle ground where they say very little, waiting for consensus that might never come because the object is already gone. The similarity is striking. We live in a universe full of signals, many hidden, many ambiguous, many buried in noise, where extraction requires sophisticated techniques and patient analysis. 3I Atlas might be a loud exception, an interstellar visitor that should be obvious and should generate clear, unambiguous data. But what if it's not? What if it's just another whisper in the stadium and we're straining to hear it over all the other noise? There's a philosophical question lurking here. How many anomalies do we walk past because they don't fit the canonical story? Dark matter itself was an anomaly for decades before it became accepted. Fritz Zwicky proposed it in the 1930s based on observations of galaxy clusters. He called the missing mass dunkle materie, or dark matter. The scientific community largely ignored him. It wasn't until the 1970s when Vera Rubin's rotation curve measurements made the case undeniable that dark matter became mainstream. Decades of anomalies were dismissed or explained away until the weight of evidence became too great to ignore. Could 3I Atlas be following a similar trajectory? An anomaly that's currently being dismissed or minimized, but that future observations or reanalysis will reveal as significant? Or is it the opposite? An anomaly that looks interesting now, but will be explained away as our understanding improves. We won't know for years, maybe decades. The story of dark matter teaches us that patience is sometimes required. Not every anomaly resolves quickly, and some mysteries take generations to solve. But it also teaches us something about the sociology of science, how anomalies that challenge existing frameworks get treated with skepticism until they can't be ignored anymore. Zwicky was right, but he was dismissed as eccentric, his ideas not taken seriously during his lifetime. Rubin faced gender-based discrimination on top of scientific skepticism. The path from anomaly to accepted fact is not smooth. It's jagged and political, influenced by factors that have little to do with the data itself. 3E Atlas exists within that same sociology. Claims about its anomalous nature get filtered through the same dynamics that filtered dark matter claims. Who's making the claim? What's their reputation? How does the claim fit with existing theories? What are the political and professional risks of taking it seriously? These questions shape how anomalies are received, independent of their actual validity. In our next part, we're going to bring in a new player, artificial intelligence. AI is transforming how we process astronomical data, how we flag anomalies, and how we decide what's worth human attention and what can be ignored. This transformation has profound implications for stories like 3I Atlas, because increasingly, AI systems are the first eyes on new data, the first filters deciding what gets elevated and what gets dismissed. And that's introduces a whole new layer of complexity to the question of silence and signals. Part 13: AI's role in the cosmic watch. The universe generates more data than humans can process. Every night, telescopes around the world capture millions of images. Every second, radio telescopes record gigabytes of signals. Spectroscopes produce thousands of spectra. The volume is overwhelming, far beyond what human astronomers can examine individually. So we've built gatekeepers, artificial intelligence systems that process this flood flag, what's interesting, and filter out what's not. These systems have become a central infrastructure, the first line of analysis between raw data and human eyes. China's 500-meter aperture spherical telescope, FAST, the world's largest single-dish radio telescope, has been upgraded with AI processing pipelines specifically designed to hunt for anomalies. The system analyzes incoming radio signals in real time, comparing them against templates of known sources, flagging anything that doesn't match. It's looking for transients, bursts, and patterns that might indicate technological signals. Similar AI systems are being deployed at other facilities as well. The upcoming Vera Rubin Observatory will use machine learning to process its massive survey data, automatically identifying supernova asteroids, variable stars, anything that changes or appears unexpectedly. NASA has integrated AI into multiple data pipelines. The James Webb Space Telescope uses machine learning for scheduling optimization, determining which targets to observe when balancing scientific priorities against operational constraints. Ground-based surveys use neural networks trained to distinguish asteroids from stars, real objects from artifacts, and interesting transients from ordinary background fluctuations. AI doesn't make final decisions, but it narrows the field and directs human attention to the small fraction of data worth detailed examination. This is efficient, even necessary. Without these filters, we would drown in data and miss important discoveries because they got lost in the noise. But AI introduces a new kind of fragility. What if the AI filters out something important? What if its training data didn't include examples of whatever new phenomenon is occurring, so it misclassifies it as uninteresting? What if a truly anomalous signal, the kind we should care most about, gets flagged as error and automatically discarded? Machine learning systems learn from examples. You show them thousands of images of asteroids, teach them what asteroids look like, and they learn to recognize asteroids, but they also learn what not to look for. If 3i Atlas showed features unlike any comet in the training set, an AI system might flag it as suspicious or dismiss it as corrupted data. The outcome depends on how the system was trained, what its confidence thresholds are, and how it handles edge cases. Let's walk through a speculative scenario. Imagine an AI system processing images from Mars. Orbiters early in 3i Atlas's approach. The system sees a faint object, tries to classify it, and finds it doesn't match any known category very well. It assigns a low confidence, flags it as a potential artifact, and relegates it to a low priority queue. By the time a human analyst looks at it, weeks have passed, the observation window has closed, and the object has moved on. The AI didn't intentionally suppress anything. It just followed its programming, its learned biases about what's real versus what's noise. But the effect is the same as deliberate suppression. Information that should have been elevated got buried. Or consider the opposite scenario. An AI flags 3i Atlas as highly anomalous, assigns it high priority, and immediately routes it to human analysts. The humans look at it, see the same ambiguous data we've been discussing, and decide the AI overreacted. They downgrade the priority, file it away, and move on to things they consider more important. Here, the AI did its job correctly, but the human filter killed the signal. The system failed not because of AI limitations, but because of human judgment applied too conservatively. These scenarios highlight an important issue. Do we trust AI pipelines more than human-led observations? Both have failure modes. Humans have biases, limited attention, and a tendency to see what they expect to see. AI, on the other hand, has training limitations and inability to generalize beyond its examples, and no common sense to fall back on when facing truly novel situations. Ideally, we'd use both in complementary ways, AI for breadth and speed, humans for depth and judgment. But that requires good communication between the systems, and the communication isn't always perfect. There's another layer to consider: AI as a gatekeeper in deciding what becomes public. If an AI system flags something as highly anomalous, but the anomaly is ambiguous or potentially sensational, the team controlling that AI system faces a choice. Do they immediately release the finding, triggering public interest and scrutiny, or do they investigate privately, first verify it before announcing and control the narrative? The AI has done its job by flagging the anomaly, but humans ultimately decide what to do with that flag. In the future, this dynamic will intensify as AI systems become more sophisticated, handling more of the data pipeline autonomously. The human role will shift from direct observation to oversight, monitoring the AI monitors. When that happens, silence might not be human anymore. It might be algorithmic, a consequence of how systems are designed and trained, rather than conscious choices made by scientists or administrators. And that introduces new accountability questions. If an AI system misses or suppresses something important, who's responsible? The programmers who designed it, the institutions that deployed it, the training data that shaped its behavior. 3ERBI Atlas was observed during a transition period. Some data processing was automated, while some relied on traditional methods. Some facilities had sophisticated AI pipelines, while others used manual methods. This heterogeneity creates gaps, places where information might slip through or get lost in translation between systems. It's not anyone's fault necessarily. It's simply the messy reality of infrastructure in transition. Old methods coexisting with new ones, neither perfect, both introducing different kinds of errors. In our next part, we're going to shift from the systems that detect signals to the nature of the signals themselves. Specifically, we're going to explore quantum communication, a leap in technology that might explain why certain signals are invisible to us. Because maybe the silence isn't about what's being said, but about how it's being said through languages and channels we don't yet have the vocabulary to hear. Maybe 3i Atlas is screaming, but we're just not listening at the right frequencies. Part 14, Quantum Communication Leap. 2025 witnessed breakthroughs in quantum communication that most people barely noticed. Satellite-based entangled photon experiments set new distance records showing that quantum encryption keys could be shared between continents with near-perfect security. Ground stations in China and Europe successfully established quantum links that conventional eavesdropping methods couldn't penetrate. This technology, which had previously been confined to laboratory demonstrations, quietly transitioned into practical deployment, marking a revolution in how information can be transmitted securely and invisibly across vast distances. For those unfamiliar, quantum communication relies on the strange properties of entangled particles. When two photons are entangled, measuring the state of one instantly affects the state of the other, regardless of how far apart they are. This doesn't violate the theory of relativity, as it's not faster than light communication in the traditional sense. You still need a classical channel to complete the protocol, but what this enables is fundamentally secure communication. From an outside observer's perspective, it's nearly undetectable. You can't intercept an entangled photon stream without disturbing it, and when the stream's disturbed, it's immediately obvious to the legitimate parties involved. Now imagine applying this concept to interstellar communication. Consider a civilization far more advanced than ours, one that's mastered quantum entanglement on cosmic scales. They could establish communication channels between probes and homeworlds that would be completely invisible to anyone not part of the entangled network. From our perspective, looking through radio telescopes or optical telescopes, we would see nothing. No signals, no transmissions, no evidence of any communication. The probe and its controllers could be in constant contact, exchanging vast amounts of data, and we would be completely blind to it. This is not science fiction. The physics behind quantum communication is well understood, even if the engineering for interstellar distances is far beyond our current capabilities. If a probe like 3I Atlas were using quantum communication, we wouldn't detect it unless we happened to intercept and measure one of the entangled photons. And even then, we wouldn't be able to decode the information without knowing the encryption scheme. From our point of view, the channel would appear silent, not because nothing is being said, but because we're looking with the wrong kind of eyes. In addition to quantum communication, highly directional, low-power laser links offer another way for signals to remain invisible. Instead of broadcasting radio signals in all directions, something early technologies did, because it was simpler, an advanced civilization would likely use tight beam lasers to send information directly to their target. These beams would be incredibly narrow, perhaps on the scale of microradians or even nanoradians, illuminating only a tiny patch of space. Unless we happen to be in that patch, unless the beam sweeps across Earth during our observation window, we would never detect it. The energy efficiency of such systems is highly compelling. Broadcasting radio waves spherically means most of the signal dissipates into empty space, effectively wasting energy. By pointing a laser beam directly at the target, nearly all the energy goes where it's intended, significantly reducing the power requirements. For a probe operating on limited energy, this efficiency might be a necessity rather than a luxury, so the probe could be constantly communicating, but only in directions we can observe. The beams could miss us entirely, or they could be so faint by the time they reach us that they're lost in the background noise of space. Spread spectrum techniques borrowed from military communications offer yet another method for hiding signals. A message can be spread across an extremely wide frequency range so thinly that at any given frequency, it looks like random noise. To decode the signal, you need to know the spreading pattern, the key that tells you how to reassemble the distributed pieces. Without that key, even sophisticated receivers would only see random fluctuations indistinguishable from thermal noise or cosmic background radiation. Traditionally, CT, the search for extraterrestrial intelligence, has focused on looking for narrowband signals that clearly indicate a technological origin because they're too narrow to be produced by natural processes. But if alien communications rely on spread spectrum techniques, we would miss them completely. These signals could be all around us, but we would perceive them as noise because we don't have the decoding pattern. It's like trying to understand a foreign language you've never heard before. At first, it sounds like meaningless chatter until you learn the grammar and vocabulary. Human radio and television broadcasts leak into space inefficiently, a byproduct of our immature technologies. We're moving toward fiber optics and directional transmitters that reduce our electromagnetic footprint. An advanced civilization would have made this transition long ago. They wouldn't leak signals indiscriminately. Instead, they would communicate precisely, efficiently, and invisibly to outsiders. From their perspective, broadcasting broadly would be akin to shouting your secrets in a crowded room, inefficient, and potentially dangerous if there are hostile listeners. So when we search for signals from 3i Atlas, we're looking through the lens of our own methods and assumptions about how communication works. We look for radio transmissions, optical flashes, or anything we know how to detect. But if 3i Atlas is using communication methods beyond our current technology, we could be standing in the middle of a conversation and never even know it. The silence we perceive is not a lack of communication, it's a reflection of our own technical and conceptual limitations. This has profound implications for how we interpret the silence surrounding 3i Atlas. Agencies may not be withholding information. They might simply have nothing to report because they're looking with the wrong tools. The object could be broadcasting constantly a beacon, visible to anyone with the right receivers. But we don't have those receivers yet. It's like someone from the 19th century trying to watch television. The signals are there, filling the air, but without the right technology to decode them, we'd never know. There's a humbling lesson here about the limits of knowledge. We tend to assume that if something exists, we'll eventually detect it, given sufficient effort. But that assumption only holds if the object cooperates with our detection methods, if it exists in a form we're prepared to recognize. Quantum communication directional lasers and spread spectrum encoding, these aren't exotic, impossible technologies. They're extensions of the technologies we already possess, refined and optimized by civilizations with more time experience and resources than ours. And these advancements make traditional CT approaches potentially obsolete. If alien civilizations have already transitioned to methods we don't yet understand, then our search for signals using outdated technology might be searching for things that no longer exist. This flips the narrative. The search for extraterrestrial intelligence is now more difficult, possibly harder, than we could have ever imagined. If we can't detect the signals because they're using technologies we don't have, how do we ever find them? The answer may be that we don't, at least not until we develop those technologies ourselves. Or perhaps we might encounter a civilization that deliberately makes their communication detectable to less advanced observers, simplifying their signals so we can find them. Whether 3 Atlas represents such a deliberate decision for visibility remains an open question. In our final part, we're going to turn the lens around entirely. We'll explore our own silence, the decisions we make about what to disclose, what to withhold, and what to emphasize or downplay. Ultimately, the silence surrounding 3i Atlas may be less about the object itself, and more about us, our fears, our institutional structures, and our choices about how to handle the unknown. Understanding this human dimension is essential to understanding the entire story. Part 15, the meta takeaway. Our own silence. We've circled around this question for 15 parts now, examining 3I Atlas from every angle: the object, the observations, the agencies, the technologies, and the possibilities. But perhaps the most important question isn't about 3I Atlas at all. Maybe it's about us. Why are we silent? Not the specific agencies or individuals involved, but we as a civilization, we as a species trying to understand our place in a cosmos that's far stranger and more complex than our ancestors ever imagined. The silence surrounding 3I Atlas may ultimately be ours, not the object's. The object is what it is, whether it's a comet, a probe, or something in between. It doesn't choose how to reveal itself beyond whatever physics or engineering determines its observable properties. But we as humans choose how to observe, how to interpret, and how to communicate what we find. And those choices are shaped by factors that have nothing to do with the object itself. Institutional pressures, funding concerns, career considerations, fear of ridicule, fear of panic, and strategic calculations that prioritize control over transparency all come into play. Let's address the ethical questions first. What should scientists publish versus withhold? The traditional answer is everything subject only to peer review and verification. Science advances through openness, through sharing data and methods so others can replicate, challenge, and extend. But that ideal bumps up against practical realities. Some discoveries have national security implications. Some findings, if released prematurely, could cause public harm through misinterpretation or panic. Some data is proprietary, collected using instruments or methods that a competitive advantage depends on keeping secret. The tension between openness and these countervailing pressures is not easily resolved. Who gets to decide when an anomaly is safe to reveal? In democratic societies, the public theoretically decides through elected representatives who oversee scientific institutions. But in practice, decisions get made by unelected administrators, scientists with institutional affiliations and funding agencies that set priorities. The public learns only what filters through these layers, what survives the review processes, what gets deemed suitable for general consumption. This isn't necessarily sinister, it's how complex societies function, but it creates a distance between discovery and disclosure. And in that distance, information can be shaped, delayed, or lost. How do national security concerns, public panic risks, and funding pressures shape disclosure enormously? A space agency considering whether to announce an anomalous finding must game out the consequences. Will Congress respond by increasing their budget to study the anomaly, or will they cut funding because the agency looks unreliable? Will the public engage constructively, or will conspiracy theories and panic dominate the reaction? Will international partners share more data, or will they close ranks and withhold? These are questions that have real answers, answers that affect careers and institutions, and they influence behavior in ways that slow or stop disclosure even when no formal suppression is intended. Bring in analogous controversies from 2025. In genetics, debates raged about when and how to release findings about hereditary disease risks. Release too early before therapies are available, and you create anxiety without offering solutions. Release too late, and people who could have benefited from early screening miss opportunities. In artificial intelligence, researchers debated whether to publish certain algorithmic advances that could be weaponized or used for surveillance. In climate science, questions persisted about how to communicate projections without either understating risks or paralyzing the public with doom. These are not simple questions with obvious answers. They're judgment calls that reasonable people disagree about. And 3i Atlas falls into the same category. If observations suggest something genuinely anomalous, something that might indicate intelligence, when and how should that be announced? After verification is complete, after international consultation, or immediately to allow global participation in further observation. There are arguments for each approach, and choosing wrongly can have consequences. The reality is that delays are often structural, not intentional. Large institutions move slowly. Data has to be processed, analyzed, and reviewed by multiple parties before it's ready for publication. This takes time, especially for complex or unusual findings that don't fit standard templates. What looks like suppression from the outside might just be the normal pace of institutional work slowed further by the extraordinary nature of the finding. Bureaucracies are not designed for speed. They are designed for thoroughness, for minimizing errors, and for covering institutional liability. Those design goals often conflict with a rapid disclosure. Now circle back to 3i Atlas. If we assume silence is evidence of suppression, we need to be cautious of falling into a self-fulfilling prophecy. The longer agencies stay quiet, the more suspicious their silence appears. The more people assume something is being hidden, and that assumption then colors how any eventual disclosure is received. If agencies finally release data showing that 3i Atlas is just a comet, unusual but natural, skeptics will claim a cover-up selective disclosure and hiding the more intriguing details. If they release data showing anomalies, critics will ask why it took so long. The silence creates a no-win situation where institutional credibility suffers regardless of what the truth turns out to be. This is the paradox of conspiracy thinking. It's unfalsifiable. Evidence against conspiracy gets interpreted as part of the conspiracy. Lack of evidence gets interpreted as successful suppression. The only way to break this loop is radical transparency, releasing everything immediately. But that has its own costs and is often impossible given legitimate privacy, security, or verification concerns. Institutions therefore are trapped, unable to satisfy skeptics without compromising other values they're supposed to uphold. So moving forward, vigilance dictates that every silence be questioned, but responsibly. Question why agencies delay, why data isn't shared, why certain findings get emphasized while others are minimized. But also recognize that not every delay is nefarious. Not every silence is suppression. Sometimes silence is caution. Sometimes it's uncertainty. Sometimes it's just the slow grinding of institutional gears. Distinguishing between these requires looking at patterns over time, tracking records, and seeing whether agencies eventually disclose or whether information only emerges through leaks and pressure. For 3i Atlas specifically, the responsible stance is to remain alert, monitor what agencies release, push for open data policies that make raw observations available to independent researchers, and support initiatives like the Galileo Project, which aim to create parallel, transparent observation networks. Demand accountability when delays seem excessive or explanations seem inadequate, but also extend some benefit of the doubt, recognizing that ambiguous data genuinely creates difficult choices about what to say and when. The broader principle applies beyond this one object. We're entering an era where our instruments are sensitive enough to detect things we don't immediately understand. Fast radio bursts, for example, appeared from nowhere in the data challenging our theories. Gravitational waves opened a new window on cosmic events that we had only imagined. The more we observe, the more anomalies we'll find. And each one will create these same tensions between disclosure and caution, between speculation and verification. Our choices about how to handle these tensions will define what kind of scientific civilization we become. Do we embrace transparency, accepting the messiness and uncertainty that comes with it? Or do we prioritize control, accepting the suspicion and delayed progress that it creates? There's no perfect answer. Every approach has trade offs, but being conscious of those trade offs, making them explicit, debating them openly, that's essential. In the quiet between the stars, the loudest truth might already be waiting for us to listen. But listening requires more than instruments. It requires courage. The courage to hear things that challenge our frameworks. The courage to sit with uncertainty rather than rushing to premature conclusions. The courage to say, I don't know, when we don't know, instead of inventing reassuring stories. It also requires trust. Trust that others are also trying to understand. Trust that institutions, however imperfect, are acting in good faith most of the time. Trust that truth will eventually emerge if we keep questioning, keep observing, keep demanding. Accountability. 3 Atlas will recede into the distance, eventually too faint for even our best instruments to track. But the questions it raised will remain. What are we willing to see? What are we prepared to acknowledge? How do we balance caution with curiosity, responsibility with transparency? These questions don't have final answers. They're questions we'll keep asking with every new discovery, every new anomaly, and every new visitor from beyond our solar system. So we monitor agency releases, stay curious, demand open data support, transparent science, but also practice epistemic humility, recognizing the limits of what we know and what we can know with current technology and methods. The universe is under no obligation to make itself easy to understand. It's vast, old, strange, and operates on scales and principles that humble our pretensions to mastery. 3i Atlas is one tiny thread in that cosmic tapestry, and whether it's natural or artificial, whether it's ordinary or extraordinary, it reminds us that we're still at the beginning of our journey to understand this incredible universe we inhabit. The silence will break eventually. It always does. Data will accumulate. Interpretations will sharpen. New observations will constrain possibilities. Maybe we'll confirm it's a comet, unusual but natural, and move on to the next mystery. Maybe we'll find evidence that genuinely challenges our understanding, forcing us to expand our conception of what's possible. Either way, the process continues. We observe, we question, we debate, we slowly build toward understanding. That's the scientific project. Messy, slow, and imperfect, but still the best method we have for navigating the unknown. And in that navigation, silence is not the enemy. Imposed silence, deliberate suppression, that's the enemy. But the silence of caution, of verification, of taking time to understand before speaking, that silence has its place. The art is knowing the difference and demanding accountability when the wrong kind of silence prevails. With 3i Atlas, that art is still being practiced. We're still in the middle of the story, not at its end. And how the story concludes depends not just on what the object is, but on what we choose to do with the information we gather. So we wait, we watch, and we question. We hold our agencies accountable while recognizing their constraints. We push for transparency while understanding the complexities that sometimes require caution. We remain open to extraordinary possibilities while demanding extraordinary evidence. And through all of this, we remember that the greatest silence we must overcome is not out there among the stars, it's within ourselves. The silence of assumptions, unquestioned of curiosity, suppressed of wonder, lost to cynicism or complacency. The universe is speaking. Whether through Three Eye Atlas or a thousand other signals, it's telling us we're not alone in space and time. We're part of something far grander and stranger than we yet comprehend. Our task is to listen, truly listen, with all the tools and wisdom we can muster, and to keep listening even when the silence feels overwhelming, even when answers seem impossibly distant. Because in that persistence, in that refusal to stop questioning, lies our best hope of finally hearing what the cosmos has been trying to tell us all along.